In this video, I will be showing you how to use Microwave Office to simulate filters. And I thought that the best way to demonstrate this was by using an example that comes from your example sheets. So you can see how the simulation can be an aid for you to verify your answers or to just play around with whatever topology and filter specifications that you would like to test. So in question 1 of examples sheet 1, we are asked to design a 4th order Butterworth filter using the ladder network realization with a cutoff frequency of 10 to the 4 radians per second and terminating resistances of 50 ohms. The first step in the design, of course, is to find a normalized low-pass filter, and this is shown in the solutions to the example sheet. So what we're going to do now is simply set up the normalized low-pass filter and see that it's got the response that we expect. So the first thing we do is right-click on Circuit Schematics and we create a new schematic. We'll call this normalized low-pass. And then what we do here is simply put all the elements that we need to create our filter schematic. Let's start with stuff that is nothing to do with the filter itself. We need to have a signal source and then a source resistance and a load resistance. So we can put those on. To find the circuit element, simply press Ctrl L and this window comes up, which allows you to search for it. If you know the name already, you can simply type in the name and it'll come up. Notice that there is a funnel here. At the moment is on the name, so whatever you put in the search box here, it will look for the name of the element. But if you change the funnel, if you move the funnel to the description heading, then you'll be able to look for something based on the description. For example, I know that an AC voltage source is ACVS, and so I'm searching for name and is finding ACVS pretty quickly. Also, I could have simply moved the funnel to the description heading, and you do that by doing Control and click. You can see the funnel now is on the description heading, and I can simply type in here AC voltage, and you can see that ACVS comes up all the same. So if you know the name of the element, it's easier to search by name, but if you don't know it and you want to look for the description, just simply Control click on the heading and type in what you need to look for. So I'll then click on OK and place my AC voltage source in the schematic like so. I'll then need to put a ground reference. You can use Ctrl G to create this, or simply click on the ground up here in the toolbar and then place it like so. Then I need a resistor, which will be my source resistance, and I'll simply click Ctrl L again and then type in RES. I'll search by name and then I get the RES element here, which is the one that I need, and connect it to the voltage source like so. I'll change the ID of this element to RS. You don't have to do this, but it makes life easier if you give the elements the right name. So now I've got a voltage source with an internal resistance of RS equals to 1 ohm. And this is the configuration that we have when we construct a low-pass prototype with a ladder network, as you have in your notes. Then I can simply click on this element, press Ctrl C and then Ctrl V to create a replica. And then I'll simply rotate it like so by right-clicking on the mouse and then place it somewhere else along here, change the name to RL, and again I'll keep it to 1 ohms because this is the normalized ladder network that we're trying to implement. I'll then again get myself a ground, so I have a ground reference at this side of the resistor. This is a 4th order filter, so now I need 4 reactive elements to be able to implement it. With the ladder network, as you know, we use capacitors and inductor alternately with the capacitors in shunt. So let's press Ctrl L again and type in CAP, which is cap, stands for capacitor. We double click on it, we right click so that we can rotate it, and then we place it in shunt like so. Then we press Ctrl L again and we find ourselves an inductor. I type in IND down here and then I double click on the element and then I place it in series just like that. When you want to connect elements together, you simply hover over the terminals with the mouse and the wiring tool appears. So then you simply click on the first place where you want to start the connection from and then on the second place where you want it to end, and this creates a connection. So now I need one more capacitor and one more inductor. I simply click on this capacitor, press Ctrl C and Ctrl V and create a replica. And then I can do the same for the inductor. Press Ctrl C and Ctrl V and create yet another replica. And then you can use the wiring tool to simply wire everything together. Now you can see that the units for inductors and capacitors are set to nanohenries and microfarads respectively. I don't want that for my low-pass prototype because I know that my values are going to be in henries and farads. So what I can do is simply go onto the Project tab here, double-click on Project Options, and then select the Global Units tab. And I can select my capacitance to be in farads and my inductance to be in henries. Now I can more easily assign values to my elements. I'll just move things around a little to tidy up. And then I can change the element values to what they need to be. The first shunt capacitor is 0.77 farads, the first series inductor is 1.85 henries, and then the second shunt capacitor is 1.85 farads, and the second series inductor is 0.77 henries. You may notice that I haven't yet set a specific frequency range for my voltage source. And the voltage source does not feature here amongst its parameters anything to do with frequency. And the reason is that the frequency for all voltage sources and all current sources can actually be set globally. And we can go to Project Options up here, and then we go to the Frequencies tab, and we can select a range of frequencies that we want to use. Once we select a range of frequency in this particular tab, what happens is that they will be used for every simulation in the circuit. Remember that this is a low-pass prototype, and hence our cutoff frequency will be 1 radian per second. In light of that, we can simply set the units here to hertz for our frequency so as to make sure that we capture the right frequency range. Then we have to select a suitable frequency range. Remember that our cutoff frequency is 1 radians per second. This is equivalent to 0.16 hertz. And hence we must make sure that we get the right frequency range to capture that. So I think that a good frequency range to use would be something like 0.001 hertz. So we're going 2 decades below our corner frequency, and then we can have 10 hertz as our final frequency. In terms of the step, you can define a range in a linear fashion, so you will have a specific step between each frequency, or, as it is more useful in the case of filters and frequency responses, you can set a logarithmic scale. So I can simply select logarithmic here, and then all I'm asked for is how many points do I want per decade. I will just set the points to be about 100 per decade. This should give us enough accuracy. Then you have to make sure that the replace option is selected and click on Apply. Now you can see that you've got a range which comprises of 400 points set up in a logarithmic scale. So you're starting from 0.001 and you're going up to 10 Hertz. Then click on OK. Now, because we set this range of frequencies globally, this would apply to any other schematic that has got a source of this type in it. And we'll see how we can select a specific frequency range for each schematic later on. Now we need to insert some elements in our circuit schematic that allow us to carry out measurements. Particularly, I want to measure the load voltage here, and I want to measure the source voltage here. One of the easiest ways to do this, you can do it in many ways, but one of the easiest ways is to use a measurement probe. And you can find the measurement probe right up here. So just click on the measurement probe icon, and then place your probe on an element terminal. Make sure that you place your probe on the element terminal. Don't place it on a wire. You couldn't, for example, do this. This wouldn't work. It needs to be right on a green square, so right on the terminal of an element. And then I'll change the name of the probe as well, and I'll change it to VIN. And I can use Ctrl C and Ctrl V for probes as well. So I can click on it, press Ctrl C, then Ctrl V, and then place another probe here so as to capture the load voltage, and I'll rename this VL. So now I've set up the right range of frequency for my normalized low-pass prototype. I've got a way to measure the load voltage and the source voltage, and what I want to see is the gain of this filter, or the frequency profile of this filter in terms of magnitude. So the next thing that we need to do is to go onto Graphs on the Project tab, right-click on Graphs, select a new graph, and then we'll call this normalized low-pass magnitude. We select a rectangular graph and click on Create. Then we right-click on the graph, we select Add a new measurement, and then we have to decide what measurement we want to add. We can collapse the linear measurements here and go on to non-linear. Then we'll have to deal with voltages, of course, and what we want to evaluate is the voltage gain. Microwave Office is excellent in this particular respect because it allows you to select the gain of a circuit between an input point and an output point, and it just works out the gain between those 2 points. So if I can just click on vGain, then I can select the data source that I want this measurement to come from. In this case, we've only got one schematic, so this is what it is. If we had more than one, we'd have to select it from here. Then it's asking you what is the voltage in component and what's the voltage out component. And if we don't remember it, simply click on the 3 dots. It'll take you to the schematic, and then you could just say, well, is this probe here? Click on it, click on OK, and that's your input voltage selected. Then for the voltage output component, you can simply do the same. Click on the 3 dots and select this probe here, which is giving you the voltage across the load, and then click on OK. Now there is something else here which may be slightly cryptic to you, the voltage harmonic index. The thing is, Microwave Office is used to working with nonlinear circuits, and hence you may have harmonics. You may want to see the behavior of a circuit at a specific harmonic component. In your case, you just want to see the behavior of the circuit at the fundamental frequency. So simply select 1 here, and this will give you the fundamental. So you do this for both of the in and output voltage. Select your harmonic components to be 1. This will just look at the fundamental frequency. And this is the range of frequencies that we selected earlier in the project options. Then you of course want to look at the magnitude or the voltage gain. Of course there will be a phase shift as well. And you can even select it to be in dB. And you may wonder, well, is it going to do the 20 log 10 or the 10 log 10? Actually, Microwave Office is very intelligent. It knows that you're working with voltage, and hence when you select dB, it will do a 20 log 10 of the voltage gain. Then you click on Apply, and then OK, and then Simulate. You can see that the graph that you get at the moment doesn't look particularly easy to read, and this is because we selected a logarithmic range of frequencies, but we are using a linear axis on the x-axis. So what we need to do is right click on the graph, go on to Options, and then you can see there we are already in the Axis tab, and what we need to do is simply tick log scale for the x-axis. Then click on Apply and OK. We move the legend a little bit further out so that it doesn't cover our graph. And you can see that now you've got a very familiar graph for a low-pass filter. So let's do a few measurements to make sure that we've got the right response here. A very useful feature of Microwave Office is that you can insert markers. And you can do so by simply right-clicking on the graph and going on to Add Marker. Or you can simply press Ctrl M, and this will allow you to place a marker. So you press Ctrl M and then click anywhere on the graph, and there you get your marker. Of course, this graph is on a log scale, so we can't really see the zero frequency because of the way the logarithmic scale works. However, if we just take this marker all the way down here, we're looking at the gain at 0.001 Hz, and this will give us a good indication of what the gain at 0 Hz would be. Now notice that our units at the moment are megahertz for our frequency axis. This is not great really, is it? Because we set our frequency range in Hertz. We can change this by going to Project Options yet again, and then again we can go into Global Units tab and select the frequency to be in Hertz. Now you can see that our graph has disappeared. We need to resimulate to get things to reappear again. Now we change the frequency units to Hertz. Now what we want to find is our 3 dB cutoff frequency. And to do this we want to place another marker. Remember, you just press Ctrl M and then you click on the graph anywhere you like. And then what you want to find is the 3 dB cutoff frequency. To do this, Microwave Office has got some really interesting features. We can set our reference gain to the gain measured by this marker, and then find the point where we drop by 3 dB. So we'd right click on that and we make this a reference marker. And then we want to find a delta of -3 dB. You can see that once this becomes a reference marker, everything else will be displayed as a delta. Now we can right click on this marker here, and then you can do a marker search. This little window opens up, and what you want to find is a delta. We want to find it on the y-axis, and we want the value to be -3. The last thing that you have to determine is whether you want to search right or whether you want to search left. If I do a search right, it won't find it because it's already too far. So you select search left and then click on search. And there we have it. We've found our 3 dB cutoff frequency. Note that our 3 dB cutoff frequency is 0.157 Hz, so about 0.16 Hz, which is the equivalent of 1 radians per second. And this is exactly what we wanted. We wanted to have a cutoff frequency for a normalized low pass of 1 radians per second. The other thing that we may want to check out is whether we have the right attenuation out of band. So we may want to have a look at the slope of the gain outside of the passband to see whether this is indeed what we expect. In this case, we have a 4th order filter. And remember that the attenuation is given by -20 times n, where n is the order of the filter. In our case, n is equal to 4, so -20 times 4 is -80 dB. So our attenuation out of band should be -80 dB per decade. So we can place another marker, just press Ctrl M and then click, say, right there, and Ctrl M and click somewhere else on the graph. And then we can take one marker all the way down here. We can remove the reference marker now from here. And we want to make sure that our markers here span a full decade so that we can see directly what the slope of our line is. I want to place this directly on 1 Hz, and it may be difficult to just move it there. You can click on it and move it to 1 Hz. But what you can also do is simply right click, go on to marker search, and then say find X value, and it's an absolute value in this case, and I wanted to find the 1 Hz point. And then click on search, and as you can see, it's found the 1 Hz point. The 10 Hz point is easy to find because it's right at the end of the graph here. Now what I can do is turn this into a reference marker by right clicking and selecting reference marker, and now I can see that my delta is -80 dB. So I've got -80 dB drop over a decade, which is -80 dB per decade as we expected. The next thing that we want to do is take a look at the denormalized response. So what we need to do is have an identical circuit topology to this one here, but of course we need to change quite a few values. So what's the best way to go about this? Well, let's use a few tricks. Firstly, we can right click on the schematic that we've got at the moment in the project option and just say duplicate, and this duplicates our schematic entirely. Then we right click and we click on rename, and then we'll call this denormalized low pass. Now we need to change a few things here, well, more than a few things. Firstly, the source and load resistances. This should be 50 ohms. So let's change those two right away. And then the values for inductors and capacitors. Now the problem that I've got here is that the units are set to henries and farads, and what I've got is microfarads and millihenries. So I can go to project options again and then go on to global units, and then I need to change the capacitance to microfarads and the inductance to millihenries, and then click on OK. Notice, however, that when you do this globally. You can't have one unit for one schematic and another unit for another schematic. And now I need to set the capacitor values for my first shunt capacitor to 1.54 microfarads. I want to have my first series inductor to be 9.25 millihenries. The next capacitor is 3.7 microfarads. And then I want my last inductor to be 3.85 millihenries. But now we have another little problem. Remember that this voltage source will have a frequency range associated with it, which is set in the project options under the frequencies tab. And this is way too low a frequency for us to operate now, because now we've scaled our circuit up to have a cutoff frequency of 10,000 radians per second. So what I need to do, I could change the frequencies here in the global tab, but actually what's more sensible to do is just change the range of frequencies that we want this voltage source to be swept over only for this particular schematic. And this is entirely possible. simply right click on the schematic name and then go on to options. You can see that in the frequencies tab at the moment we have an option which says use project defaults, which is ticked. We can untick this and select our own frequency range for this particular schematic. I will again select the units to Hertz because this is quite intuitive, but in this case I will start from 100 Hertz and I will stop at 100,000 Hertz, and again I'll keep 100 points per decade. Since our cutoff frequency is 10,000 radians per second, which is roughly 1592 Hertz, then this range should work well for us. Make sure that replace is ticked and then click on apply and then OK. So now we've sorted out our schematic, we changed it to that of a denormalized low-pass filter. Now all we need to do is create a similar graph to the one that we created earlier. Again, we just right click on graphs, choose a new graph, a rectangular graph, and we'll call it denormalized low-pass magnitude. Then we right click on it and select add a new measurement. Now we need to select the right schematic up here. It will be the denormalized low pass. We are selecting voltage gain is again the same as before. We want the magnitude, we want it to be in dB, so all the settings are saved. We said the harmonic component should be 1, so you look at the fundamental. And then let's just check that the voltage in and voltage out components are correct. The voltage in component is indeed the one that we want, and the voltage out component is also the one that we want. So click on apply and then OK, and then you click on simulate. But what you can do yet again is right click, go on to options, and then in the axis tab tick the log scale for the x-axis and click on apply and then OK. Let's move the legend away a little bit so we can see things a little bit more clearly. And now you can see that our response has changed considerably. Of course, we are working over a different frequency range, but we can use exactly the same technique as we did before to work out the various crucial frequencies. So first of all, let's press Ctrl M and get ourselves our marker right down here, right at the bottom of the frequency range. This is not 0 Hertz, but it'll do. And then we do Ctrl M again and place the marker somewhere on the schematic, say here. Then we right click on this and we call it a reference marker. This now becomes a delta, and we right click on that and do a marker search. We want to search for a delta, find the Y value, and the value should be -3, and we'll search left. Click on search and you can see that you found your 3 dB delta point, which is your cutoff frequency. But bear in mind that at the moment we are looking at the delta both in the frequency and in the amplitude. So because here you've got 100 Hertz, then the frequency that is shown here is this frequency minus 100 Hertz, much in the same way as the amplitude shown here is this amplitude minus 6 dB. So if you really want to see the cutoff frequency, you need to take this away from being the reference marker, and now the frequency that you see displayed is the frequency that you are looking for, which is your 3 dB cutoff frequency. So this may be a tricky thing with markers. You have to be particularly careful. In the case of the normalized low pass, because the reference frequency was so low, even if you turn this into a reference marker, you can see that the delta is not going to be too dissimilar from the actual frequency. But in the case of the denormalized one, if you turn this into the reference marker, then you see you lose 100 Hertz. So be careful with that particular thing. So let's take this away from being reference marker. The other thing we can do, as we did before, we press Ctrl M, and then we place another couple of markers. We move one all the way to the end here, and then we simply right click on the other one, do a marker search, and search for an X value of, say, 10,000, which is a decade below, an absolute value, and then search. And then we simply right click on this, turn it into a reference marker, and lo and behold, we've got -80 dB per decade, which gives us the attenuation that we're looking for a fourth order filter. Hopefully this has got you started with Macro Office and with handling the various features of it which you need for filters, and you'll be able to characterize now the filters that you've got in your example sheets or in your notes, and see that you do indeed get the right response.